All right. Okay, so this is a project with Victoria Gittman on a variant of measurable cardinals, and she gave a similar talk before. So sorry to those who heard the talk, but this is probably not many. And it's a kind of miniature version of measurable cardinals. Doesn't work before. Ah, it's fine. I wasn't there. All right. So, so what I just want to do is essentially just an introduction to the field of Ramsey-like cardinals, and then the end about the result of ours. And the result is about the cardinal called N-baby measurable. This was introduced not by us, but people called Mackenzie and Bovikin to actually answer a question about a variant of new foundation. I'll say something about that. So the Ramsey-like cardinals are very versatile. They can use in many contexts. So this is an example for that. They realize they can somehow use these cardinals to understand the consistency. All right, so I have too many slides, but I'll skip over some. So here, I just want to give you an example. So by Ramsey-like cardinals, we just cardinals between weakly compact and measurable, like Ramsey cardinals, for example. But then there are also many interesting other cardinals, and I just give you a few examples here. Ramsey remarkable, ineffable, ineffable, and I put the definitions there. It's often something like a coloring homogeneity property. The original definition of ineffable is something slightly different. It's like a coherence property. And what people like to do in the field of Ramsey-like cardinals is to characterize those by elementary embedding. So we want to characterize all these cardinals more by elementary embeddings of the model. Why? Well, if you have kind of uniform characterizations of all different cardinals, it's very easy to compare them. So it's good to get an understanding. And I want to give you, I want to start with I want to give you all the definitions we need, although it's all very simple. So there's the notion of weak kappa model and kappa model. The difference is the closure. The weak kappa model is just the transitive model of CFC minus kappa. That is a bit higher than kappa. And then if it's less than kappa close, it's called the kappa model. And then actually often we're interested in submodels of some H data, and then well, then you can't have a transitive set. So we call this basic kappa model, that weak kappa model. We additionally ask it's sigma zero elementary. And then we might want it to be less. Well, it's simple if kappa is the largest cardinal. So for example, think of an elementary submodel of H kappa plus. Get a simple model. All right, then we're always going to have it accessible to avoid these kind of cardinals below the continuum with embedding properties. Sorry. All right. Sorry about that. So, okay, what about the ultrafilters? Well, so first of all, the point is basically think of a measurable cardinal, and then now instead we have this small kappa model, or weak kappa model, and an ultrafilter. But then there are many different possibilities. So in V, you just have a normal ultrafilter, or less than kappa complete is actually equivalent. But he could have many different properties. We're always going to ask that the filter is normal with respect to the model that is defined over. All right. So any ultrafilter is M normal. Right. The ultra power might not be well founded. If it is, then the filter is called good. And the point of this talk is that, well, M itself is a model of CFC minus in our case. But if you add U, it might be some very bad structure. It might fail separation collection. And I'll get to that later. All right. The point is, in our project is the more internal U is to M, the stronger properties, large cardinal properties you get. So if you ask the structure M with U to be closer to a model of CFC minus, you get a stronger large cardinal. Right. So I just saw that the titles are not visible. I'm not sure. Can I do anything about them? Ah. Good. So, okay, what about the ultrafilter? You might want to know that it's weakly amenable. So amenable means you can intersect it with the set and the model, and that intersection will be in the model. Weakly amenable means you only have that with sets of size kappa. So why do we need that? You need that if you want to iterate ultraparse. Otherwise, you take the ultrafilter U and you apply the ultrapower. It's not really defined, right? Because U is not and the model is external. But if U is weakly amenable, then there's natural definition. And then you can try to iterate that. I'll say something about that in a minute. So weakly amenable is actually equivalent to preserving the power set. So adding no new subset kappa in the set. That's what this slide says. Okay, so amenable is the same as kappa parset preserved. So again, this is going to make our property stronger, so you will get a stronger large cardinal property. All right. Okay, so let's begin with some example of the embedding property of weakly compact. Probably most of you know. I'm actually giving you four. I'm giving you four embedding properties. So just see that for weakly compact, all these different properties don't matter. You still get the same large notion. So whether you that's when you want M to be elementary in some H data, or you ask kappa close, it's still the same large. Or, well, the weakest one is 3. You want the ultrafilter well founded. That gives you the tree property. Then, okay. The reason why I chose 2 is because I said that the ultrafilter is countably complete. The only reason I chose this is you get Ramsey cardinals. You add amenable. Take 2. You add property that is amenable, then you get Ramsey, and that shows you that being amenable can strengthen the large cardinal. Example. Another example of ineffable was characterized in 1980. So the only difference to the previous characterization is now we ask the diagonal intersection stationary in B. So if you have an abnormal ultrafilter, take the diagonal intersection in the model. Okay, the model thinks this is large set, but it might be non-stationary. So that's actually strictly stronger because it gives you ineffable. So all these tiny details matter here. And so now I want to quickly talk about the result of Victoria Giffman and Philip Welsh. So as I said, if you have a weakly amenable ultrafilter, you can try to iterate it. But then, well, it might be that the first ultrapower is well founded. You can then form the second one, but that might actually be ill founded, and you get the so-called one cardinal. And actually, so Victoria and Philip separated those. They showed it. For any alpha is smaller than beta, then the largest one is actually a stronger notion. So this is a very fine hierarchy that I tried to put in the diagram on the right. As alpha increases, okay, so this part was about the property having well-founded target or target embedding or integration. Talk about 2 more properties. Next one is the closure of the target model. As an example, I want to give the participant in me called alpha Ramsey cardinals. Here, just sparing the closure properties of the target model. So as you can see in line 3, it says M is closed under alpha less than. Well, there's the technical property M should be elementary in H theta, and the ultrafilter is amenable. The point here is I was trying to get the. Okay. All right. Okay. The point here is okay. Again, look at the closure. If you increase the closure, you again get strict hierarchy of large cardinals that strict. The third bullet point is strict in direct implication. So for now the mic. So if alpha is strictly less than beta, then the beta Ramsey test. Okay. Diagram slide here. So those are the alpha Ramsey. So we're not high above the alpha cardinal. So the will exist in L. Here on the diagram, omega 1 attributes 1 L. And you have Ramsey, and so these alpha Ramsey strength. This gives you another hierarchy of Ramsey-like. Like to yes. I guess I'll quickly say that, although, and then I'll get to. So I skipped this slide. So okay, so the way how you prove this strict hierarchy. Okay, now we have. Okay, sure. Should I explain the game? Okay, so this is just to show this strict hierarchy. Let me explain the game. Challenger and the judge. The challenger plays kappa model, less than kappa close kappa model. And then the judge has to respond by playing an ultrafilter on it that just measures all the sets of the model. So the point is, if you do that for one step, you get but now you have to iterate that. So challenger plays, the judge plays an ultrafilter. Now the challenger extends the model and to extend the ultrafilter and so on. And you have to do that for alpha. And this gives you precisely the alpha Ramsey cardinal properties that the challenger does not have a winning strategy. That's equivalent to alpha Ramsey cardinal. Okay. And you can here easily see that good closure property. You have this union of models played in the game that gives you the closure property. Okay, so let's get to amenability and strengthening. This is about the model M as a predicate. So here's an example that I told you before. This characterization is weakly compact from before. You know, just add that use amenable. We now want to strengthen. Oh, here's another example where amenability is important for characterizing completely ineffable by an embedding property by holding. Okay, now let's get to baby measurable cardinals topic of our project. So let's EFCN node EFC minus restricted to sigma n formula. Sigma n separation and sigma n. Actually, collection. We're working with collection. And so we use a slightly simpler definition than what we can see, but the result they have still works. So we have three notions. A very weakly n-baby measurable says that every subset A of kappa is contained in a weak kappa model that admits the ultrafilter. So in addition, M with the ultrafilter is the model of CFC minus N. Right? So once you increase N, you get stronger property. Then weakly n-baby measurable additionally says that the ultrafilter is good. So this meant the ultrapower is well found. And you additionally ask that M is less than kappa. So it's similar to these previous characterizations, except you want M with U to be a nice. So how strong are these? That's how we ask ourselves. Let me first talk about where this came from. So they wanted to analyze a variant of new foundations that with unrestricted comprehension, but certain type formula. And there's a claim that this consistency hasn't been really verified. But NFU with UR elements, the sets without elements that might for a long time has been known to be a very weak system, and then people who work in this field be able to do mathematics because NF is very bad. You actually do math, and this is much better. And then they're asking what's the consistency strength, and Solovey showed it same as essentially model of CFC with where ord is measured. So that's the theory. Okay, I'm Billy Morse with an ultrafilter predicate. KMU is essentially the same as CFC minus with U. So you can think of this model as either ord with an ultrafilter on ord, or you can think of the model with the largest cardinal with an ultrafilter on. All right, so these are excellent. And so Holmes and Solvay showed that I think it's with the system. So, sorry, if I went, please. So let's get back. We want to understand these cardinals and see where they lie in the hierarchy of Ramsey-like cardinals. This is the theorem. Okay, so first of all, remember I had these three notions. If you take the weakest one, but you increase n, you get a stronger notion. So I think this actually works for n+1, but right now we have this in our blueprint. All right, and the ideas, this is not very hard to prove. So the n+2 baby measurable gives you this ultrafilter U. We don't know that the ultrapower is well founded, but we can work entirely with the model M. And in particular, you can construct Stoll-M halves within that model. And then in that model, you show certain powers. Then where do the line comparison to cardinal? So suppose you take the weakest one weakly. I think that should be very weakly Zer-baby measurable cardinal. Additionally, assume the GCH below that cardinal. Then this one iterable and a limit of one iterable cardinal. And I want to explain why I don't yet know if you can remove the GCH. I want to explain why this is relevant to your slide. Well, let's take the situation we have a simple weak kappa model and an immutable ultrafilter on it. And then we're ready to show that this has a delta 1 definable global well order. Go into the ultrapower, and there you can compare where in CH kappa plus in the ultrapower. There's well ordered. Then for each element, you can pick a representative in the ground model, and you can this gives you a way to compare the elements to the ground model. The problem about this well order is from the viewpoint of the model, maybe it's not set-like, but it is if the GCH CH holds at many cardinals, then well order will have ordered by cardinals of that model, and then certain recursion work with. Okay, I wanted to explain why GCH is necessary. We don't know. Okay, so here's finally a picture. We remember before we had these alpha Ramsey cardinals. Down here in kappa is kappa Ramsey. I know we're far beyond that. For the one baby measurable. So this theorem says very one baby measurable that's already about the kappa Ramsey. All right, and then you have this. Yes, actually. So, well, I just wanted to say in the paper we also study a few related notions, similar games as I showed you for the alpha Ramsey card or some cardinals. Okay, and there's just some improvements to do. Some of the results are not perfect. Still work with that, for example, divide the GPH. Another question that came to my mind I wanted to mention. Can you find a large cardinal? So now we've characterized essentially measurable cardinal, but you cut off CFC. What about CFC with a measurable? Maybe find a sequence of large cardinal notions like this that are kind of cofinal. So I don't know, might be. Okay, then the end. Okay. Yes. Oh, I see. So Matt Foreman asked, could there be versions of these kernels that, or the games, the games, the games that could be extended to stronger kernels, like strong kernels, for example? Yeah. Yeah, that's right. Yeah, I think there. I think that's a good topic to work on. So I think one. I mean, you could vary this game in the game I show the game. I think so. I haven't worked on this, but I mean, you can just change the length of the game. For example, you could try to play on p kappa lambda, right? You can take an ultra. You take a fixed lambda. You work with kappa lambda. You take. So the challenger gives you a subset of kappa lambda of 1 for kappa. So another question is, I'm not sure if you just take the simpler game where, so in each round the challenger plays 1 set, so on. I'm not sure if it might be equivalent to this game. Essentially, they might catch up after kappa mini round. Any case, so there are at least these two variants I can think of, and then you just play as long as you want. You can play you can play as long that you reach false. In the end, you would just get a normal ultra filter on it, fine filter on it. Sure. So I think it's something. Oh, it's so the speaker is online. Next is online, so yes, it's a bit hard to manage. It does. But